So just to recaps for the recording, we have an n by n matrix A, and our context is to, and goal is to compute A to the nth power for n large or even n infinite. We're going to start off with the first topic in section 2 here of the chapter on spectral theory with the definition of a diagonal matrix, which is defined to be the matrix of a given size, which only has diagonal entries. The diagonal entries are the ones where the column and row are the same. Now, as I was saying when I realized that I should record this, is that the standard basis 1, 0, 0, 0, 1, 0, and 0, 0, 1 is actually, those are the eigenvectors of this matrix, and the diagonal entries are the eigenvalues. Okay. So, with that said, the question is, so here's the strategy. Because a diagonal matrix, let's call this say diagonal matrix, say D. If I had a diagonal matrix D, it would be easy to calculate the nth power, because if I take say 2, 0, 0, 3 times 2, 0, 0, 3, you can see it's just going to be 2 times 2 plus 0 times 0 is going to be 2 squared. And then the other entries will all be, the off-diagonal entries will be 0. And the second one will be 0 times 0 plus 3 times 3, 3 squared. So the diagonal matrix is just going to be another diagonal matrix with each of the entries raised to the nth power. So this is going to look like lambda 1 to the nth power 0, 0, lambda 2 to the nth power. So this is a suggestive form that if we could convert matrix A into a diagonal form, then we could take its power, some power of it would be easy to do, right? So here's the question is then, when can you make a matrix into when can you diagonalize a matrix? Find another matrix that's somehow equivalent to it that has the same eigenvalues that that is diagonal. Now, it turns out that last time we did this idea that looked at matrices that were similar. So it's a relation between matrices of the same size. But if there's a matrix P that's invertible, P inverse, so it has to be invertible. If A and B are related in such a way, then we say A and B are similar. And it turns out that similar matrices have the same eigenvalues. So if I could find, so here's the idea. If I could find for matrix A, if I could find a similar matrix for which where B was diagonal, right? Then I'd be home free because I'd have sort of the diagonal matrix in there. Now it turns out there's some nice properties of similarity that if A is similar to itself, you just use the identity matrix here. And then if A is similar to B, then B is similar to A. Well, you can see that if I can just multiply both sides by P inverse, and then multiply on the right by P, and you found two matrices that says that B equals something like to A, and the same thing works for A is similar to B, and B is similar to C, then A is similar to C. So it's useful maybe later on to see why that's the case. So you can see it in a simple situation here. Oh, I did the same thing again. No, getting even worse. Where is There, we're down at the bottom here, okay. No, I did the right one, okay. So here we are. So let's say that A is similar to B and B is similar to C. Well, that means that A, for some matrix P1, let's say that they're that these are similar for the same matrix, right? So what we're going to have is what we're going to have here that A equals P B P inverse, and B equals P C P inverse. Okay, so they're similar, and so what's going to happen is then that if I say, well, A is this, and I can just plug B in here, A is going to equal P times P C P inverse P inverse, and that's going to equal P times C times P inverse there. And actually, I don't even think these have to be the same ones. Like if this was, I think P1, P1, P2, P2. This is 1, 1, 2, 2, 1, 2, 2, 1. Now, there's a theorem that says that the inverse of P1, P2, if P1, P2 are invertible, then it has an inverse, and its inverse is P2 inverse, P1 inverse. So this equals P1, P2 inverse. So that means that A is equal to some matrix times C times the inverse. So A is similar to C. So it's just the basic properties of inverses and similarity. And we're going to see this trick where you have two things like this and you put them together and mess with the matrices like that. Okay, is that okay? You guys see that? Okay. So now the question is, let M be an n by n matrix. M is diagonalizable exactly when there exists invertible matrix P such that this is true. So the idea here is that we want to find a matrix. So we're given M, and we want to find, if we can find a P, an invertible matrix P such that it converts this into a diagonal matrix, then we say that M is diagonalizable. And that's our goal. Now, the question is, when can this be done? Well, it turns out that if this would solve our problem, if we could find this, because if we want to find the nth power of M, we can invert this relation here, right? And so multiply both sides of the equation by P. So that would be P times P inverse MP. And then this P and P inverse will be the identity matrix. You'll have MP, which will equal MP. So that maneuver got me this far. P times D equals M times P, right? And then I can multiply on the right by P inverse, and I'll have P D P inverse equals the P inverse on the right hand side. I'll just have M. Okay, so I have this relation here, and if I do this little maneuver, I can sort of invert it to say that M equals P D P inverse. I always sometimes trying to write these down. You can forget whether the inverse should be on the left or the right. Okay, let's see. How does this help with the problem of finding the power? Let's look at the power of, say, the nth power of this matrix. Now, let's just do it. Let's just do the square first. Okay. Well, this is just M times M, right? Well, then we can just substitute this formula for M in there for each one of these M's, and we'll have P D P inverse for the first one, and then P D P inverse for the second one. And matrix multiplication is associative, so I don't really have to write parentheses or change them around. So that's why I can leave them off here. Now, if you look at this, you see I have got P and P inverse next to each other. So they cancel off and produce the identity. So I have P d times d, which is d squared P inverse. So m squared is just P times d inverse times P. So now since I can I know how to do d squared easily, just by multiplying the diagonal entries, raising each one of those to a power of 2, this is just 2 matrix multiplications. Now you can see that this is going to work for n just as well, because I'll have here n copies of m d. I'll have m copies of, m times m times m times m, and there'll be n copies. And I'll do the same thing, put this in for each of them. So I have P d P inverse, P d P inverse, and then this will be P d P inverse and P d P inverse. And you can see between each of the d's, you're going to have a P inverse P. So this is going to equal P times D to the nth power P inverse. Okay, so if we can sort of find, this situation, then we're home free, right? Because this is the solution. This would be the solution to finding the nth power of m. Okay. Now, so the question is, when can this be done? Why is okay, something, let me see if I can, yeah. Oh, that's good. There's a conflict between the graphics pen and the mouse, so I have to go back and okay. Well, so we're back on track here, I think. Distinct eigenvalues. Okay, there's some intermediate theorems here, right? And let's see if when I get the first theorem, so I make sure. Okay, here's the crucial theorem. It's on page 536. So the process is we want to diagonalize the matrix. What is this? There is a theorem that says it's called, so we want to diagonalize M is diagonalizable. And this is equivalent to, there's an invertible matrix P in which the columns are the eigenvectors of M. And so basically, if you find P and it has n eigenvectors, then you can put so it's diagonalizable if there's n eigenvectors, and you can put them where the eigenvector components are the columns. And then it turns out that this is always going to be invertible. For such a P, this is diagonal, okay? So then the eigenvalues of M are going to be the diagonal entries. So basically what we can do is, the procedure is, this theorem guarantees you take M, you find the eigenvalues, you find the eigenvectors, you can form P, calculate its inverse, form this product, and you find the diagonal matrix. Equivalently, you can just start from M, find the eigenvectors and eigenvalues, write down D, construct P and P inverse, and you can immediately then construct M to the nth power using this formula here. Okay, so so that the eigenvectors and eigenvalues solve this problem. Let us, there's an example there with the 3x3 example, and what I'd like to do is see if there's one. Now, then you can do this as long when you're guaranteed that all this works, if you have, if an n by n matrix M has n distinct eigenvalues, it is possible for the eigenvalues to have multiple multiplicities, like two eigenvalues. There's like two copies in a characteristic polynomial. There's two factors identical, so could have the same polynomial. In that case, you're not always guaranteed of having n eigenvectors. So, but we're going to stick to this case. And then there's a section on when matrices can't be diagonalized. Okay, well, let's start with this. This matrix looks particularly easy to work with. Who knows, though? Let's see what happens with this one. Let's treat, just to illustrate the procedure, let's take M equals to 1, 2, 3, 0, 0, 0, 0, 0, 0. This is problem 11 on page 554. Okay, well, we have to, let's go through. This will be a review of finding eigenvectors and eigenvalues. So what we do is we have to form the characteristic polynomial. That is, we take the determinant of 1 minus lambda 0, 0, 2 minus lambda 0, 3, 0 minus lambda equals to 0. Okay. And let's see what happens. Well, we have to use here. We can use here there's a formula for expanding a 3x3 determinant, and it works like this. You take across. It's easy. What you want to do is expand across a row or column where you have as many zeros as possible. So then you put plus, minus, plus across the top, right? And then you're just going to have let's see, do we want to do this? Maybe this matrix will, it's 0 minus here, 0 minus. This is going to have a repeated eigenvalue. So let's hold off on this because it works, but it has a repeated eigenvalue, and I don't want to have to mess with that right now. So let's choose a different matrix. Maybe we'll choose a simpler, a 2x2 matrix. That might be a simpler process for understanding what's going on. Okay. So let's try let's see if they have one that is I just want to find a 2x2 matrix that they might have gotten that might be nicer than one that I would think of that would be better. Okay. Oh, okay. Let's try well, I know this matrix doesn't also this I think this will work. We did this last time. So the 0, 1, 1, 0. Let's take M as this one. Okay, so then we take the determinant of this matrix, 0 minus lambda 1, 1, 0 minus lambda equals 0, right? And then the characteristic polynomial is just lambda squared minus 1 times 1 equals 0. So the eigenvalues are lambda equals plus or minus 1. So we'll take lambda 1 equals to the lower one minus 1, and lambda 2 equals to 1. Now I'll try to avoid making the mistake I did last time. We'll do the eigenvectors by looking at 0, So we're going to do lambda 1, which is 0 minus 1, 1, 1, minus 1. This is 0 minus 1, 0 minus 1 for this one. Okay.
Would it be positive? Minus a negative?
Yes, why do I do this? I'm making the same mistake I made last time. I can't, if I put in a 0 and do minus, so minus 1, there's some kind of bug in my arithmetic thinking there. Okay. So now this is, the problem is 1, for lambda 1 equals minus 1. It is 1, that's the matrix. So we find this equals to 0, 0. And so the augmented matrix does that, and we will then do minus row 1 plus row 2 to get 1, 1, 0, 0, 0, 0, and then the equation is x plus y equals 0, so x equals minus y. And so we can choose a characteristic eigenvalue of y equals minus 1 to get 1 minus 1 for V1. And then we can choose lambda 2. Lambda 2 is 1, which is going to produce minus 1, 1, 1, minus 1. X, y equals 0, 0. And the augmented matrix, you can bring to echelon form by row 1 plus row 2. And you've got minus 1, 1, 0, 0, 0, 0. So the equation on the components is minus x plus y, so equals 0, so x equals y. So we have V2 equals 1, 1. Okay, so that's, then we can choose that, we say P is equal to the matrix of the first eigenvector we chose, 1, minus 1, and the second one, 1, 1. Okay? And then we need to find P inverse. So, and we can go ahead and do the giant augmented matrix method. Row 1 plus row 2 produces 1, 1, 1, 0, 0, 2, 1, 1. Okay. And then we can do minus, we can do plus 1/2 row 2, get 1, 1, 1, 0, 1/2, 1/2, and that'll be 0, 1. Then we would do minus row 2 plus row 1 to get 1, 0, 0, 1. And this would be 1 minus 1/2, so we'd have 1/2 there, and then we'd have, this, the Y row wouldn't change, and then this would be minus this plus this, we'd have minus 1/2 up here. So it looks like P inverse equals 1/2 minus 1/2, 1/2, 1/2. And we should probably check that because this is 1, 1, minus 1, 1, and we multiply, that's P, we're going to put P inverse here, 1/2 minus 1/2, 1/2, 1/2. And so we don't, we can pull a 1/2 out of that matrix. This is going to be 1/2 times 1, 1, minus 1, 1 times 1, minus 1, 1, 1, which equals 1/2. 1 times 1, 1 times 1 plus 1 times 1 is 2. 1 times the first row times the second column is 1 times minus 1 plus 1 times 1. cancels in 0. The second row times the first column is -1 times 1 plus 1 times 1, 0. And the last one is -1 times -1 plus 1. 1 times 1 is 2, which equals 1, 0, 0, 1. So check. We have got that correct. Okay. Now, we have to keep the order now. D is equal to -1, 0, 0, 1. You have to keep the same order. So this is lambda 1 and lambda 2, because that's the order we chose in P. P was V1, V2, so we have to keep the same order here. Now, so we have that, so we should have that the original matrix M here zero, 1, 1, 0 should equal, right? It should equal P times D times P inverse. Well, let's check that and see. Because we could put P, it should equal P times D times P inverse. Let's check that and see, because then if that's true, we can raise M to an arbitrary power. Okay, well, so the question is this the case? Well, P is, what's P? P is 1, -1, 1, 1. The diagonal one is -1, 1, 0, 0. And this is 1/2 minus 1/2, 1/2, 1/2. And we may as well just we can check the case that if we just take put actually D to the M here, because we know that if this is true for 1, it's going to be true. So we can just let this should be just M to the nth power. Okay, well, let's see what that is. Well, this is going to be 1, 1, -1, 1. Now this will be -1 to the nth power 0, 0, 1. And 1 to the nth power is n. It's just 1 rather. And to do this, we can just, again, to make it simple, pull out the 1/2. Okay, and then we can put the 1/2 out front. And then we'll repeat this first matrix and then do the second multiplication here. And this will be, this matrix here times this one with the 1/2 out there will be -1 to the nth times 1 plus 0 times 1. That's -1 to the n. Then this one is going to be -1 to the n times -1. That'll be -1 to the n plus 1 plus 0. And the second column will be 0, 1, and then -1 times 0 plus 1. Okay? Now we have to do this last one, 1/2, 1, 1, -1, 1, times -1 to the n -1 to the n plus 1. That's just -1 to the n. 1, 1 there. So let's then do this one. Well, this would be 1 times -1 to the n plus 1. So that's 1 plus -1 to the n. Okay, the first row times the second column is going to be 1 times -1 to the n plus 1 plus 1. So that will be -1 to the n plus 1 plus 1, because it's 1 times -1 to the n plus 1 times 1 plus 1. And the second row will be -1 times this will be -1 to the n plus 1 plus 1. Okay. And the second one here will be -1 well, that this, let me see, let's do this. This one was minus times minus 1 to the n. That's minus 1 to the n plus 1 plus 1. The second one, the second row times this one is minus 1 to the minus 1 to the n plus 1. But that's minus 1 to the n plus 2. But minus 1 squared is just 1. So this is going to be minus 1 to the n plus 1. Okay, so the final result looks like 1/2 1 plus minus 1 to the n, 1/2 1 plus minus, well, we can take, maybe we should take it out here and put this minus 1 to the n plus 1 is we can put minus 1 to the n. So that we don't have, so it looks like we only have minus 1 to the n. Then this would be 1/2 1 plus minus 1 to the n. This will be 1/2 1 plus minus 1 to the n. So this should be m to the n. Now, what's going to turn out here is this is going to be much simpler if we separate the two cases of n even and n odd, right? Because then for n, let's say for n equals 2m, the even case, what will that be? Well, this will be oh, I made it, let me see. This one here is also a minus sign. That's crucial. I don't want to make that mistake. So the inverse one here comes in. Okay, so if n is even, minus 1 to the 2m equals 1, right? Because that's even. But that means this is 1 plus 1 is 2, so this entry is just going to be 1. And that's true down here too, it's going to be 1. But this entry, because this is even, would be 1, but 1 times 1 is 0. So it's just that, I think.
So would you like to explain again what you did once you got the inverse of the matrix? I understand how we kind of calculated it to figure out.
So where did we go back to?
Right there. So you multiplied p by the inverse of p?
Yes, I just wanted, this is just a check. Did I get this right? This is just a check that P inverse is correct. Because maybe I made a mistake and this wasn't, maybe I made some mistake and this looked like it's okay, but could have made some mistake. So the point was because I'm going to use that in a further calculation, I wanted to check that I hadn't made a mistake along the way.
And then the D, what happened to that?
Okay, the theorem says that here's the logic. Let's see. Find that theorem. Okay. The logic is the following. If an n by n matrix M has n distinct eigenvalues, then M is diagonalizable. So we started with our n and we found two distinct minus 1 and 1 eigenvalues. Therefore, it's diagonalizable. Now, what is the definition of diagonalizable? What diagonalizable means if n is diagonalizable, then these are two equivalent statements. It's diagonalizable, and there's an invertible matrix P, which the columns are the eigenvectors of M, namely here, and it turns out that this will always have an inverse if one, so that there's an inverse, and for such a P inverse MP is diagonal. Moreover, if M is diagonal, so the eigenvalues of M are the corresponding diagonal entries of the diagonal matrix. So since we found distinct eigenvalues, we know that this matrix here exists and will be invertible so that this is true. But then we took this and inverted it, so we have M equals P inverse MP. But then we saw above that up here, that if this is true, then we can just turn it around and see that this is true. And then we can just see that that M to the N is just going to be D to the N P inverse. So what we go back and say, okay, now that we found that M has distinct eigenvalues -1 or 1, we can form D and P from the eigenvalues and eigenvectors and just calculate this, and we'll end up with M to the N. And so we've gone through and done that laboriously.
So we found P.
We found P.
We found
We inverted it and found P inverse.
okay, and
then we started with once we found P inverse, we found D, right? So we sort of have found these intermediate results here. We found P. We found P inverse. And then we constructed D. Okay, and then
we constructed D by multiplying.
we just constructed because we just put the eigenvalues onto the diagonal entries. These are we know that it's just lambda1, lambda2.
Okay.
So we know within that this is lambda1, lambda2.
Okay.
Then, since we know this is true, and we can check it, but if we just put a 1 in here, that we'll get that's the next case. But then we say, okay, well, if this works, we can just directly calculate M to the N, and we have a formula here. So this is the actual formulaic result, but and it's hard to look at because it's got lots of crud in it, right? -1 of the. So then we said, which it's clear that it's going to become simpler if we look at the two cases. So if we look at the case even, it turns out that if N is even, you just get the identity matrix. But what if N equals 2M plus 1? Or some other M, it's going to be odd. And then the question is this, well, then what's going to happen is up here, the -1 to the 2M plus 1 will be -1. So the two entries that cancel are the diagonal entries, 0 and 0. And since I have a -1 here, this is the one that will be non-zero, so I have a 1, 1. And this actually makes sense because if I multiply, this is my original matrix M, right? And so if I choose M equals to 0, then I get the right. I want this result because I want to see that it's the same. And you can see what's happening is because it's such a trivial case that 0, 1, 1, 0 times 0, 1, 1, 0 equals 0 times 0, 1 times 1 is 1, 0 times 1 plus 0 times 1 is 0, and the second row times the first column, 1 times 0 plus 0 times 1 is 0, and the second row times second column is 1 times 1 plus 0 times 0 is 1. So it's just swapping back and forth. In other words, if I add another M on, it's just going to give me M. So it's just flipping back and forth to identity M, identity M, identity M. But although it's simple, and you didn't really do it in this case in some sense, this shows the procedure. And it shows that to do the procedure, even for a simple case, is a little bit tedious, right? Because you have to go through and find all the stuff. But we'll go and do some more examples in a second.